Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and as always, I'm joined by my brilliant co-host, Victor. Before we dive in, I want to remind our amazing listeners that if you're enjoying our content, please rate us on your favorite podcast platform. Your support means the world to us.
Absolutely, Sheila. Your feedback helps us improve and reach more developers interested in decentralized systems. Now, let's get into today's topic, shall we?
Definitely. We're currently in Season 1, Chapter 3, focusing on distributed hash tables or DHTs. Today, we'll be exploring node discovery and routing in DHTs. But first, let's start with a quiz question for our listeners. Victor, would you like to do the honors?
Of course. Here's a brain teaser for our audience. In a DHT network with 1 million nodes, approximately how many hops would it take, on average, to route a message from any node to any other node?
Ooh, that's a tricky one. It really makes you think about the efficiency of DHTs, doesn't it? I'm sure our listeners are pondering over this. While they mull it over, let's dive into our topic. Victor, could you start by explaining what node discovery is in the context of DHTs?
Certainly. Node discovery in DHTs is the process by which new nodes join the network and find their place within the distributed system. When a node wants to join a DHT, it needs to know at least one existing node in the network, often called a bootstrap node. This bootstrap node helps the new node find its neighbors and build its routing table.
That's interesting. So it's like when you're the new kid in school and you need someone to show you around. But how does the new node actually find its place in the network?
Great analogy, Sheila. Once the new node connects to a bootstrap node, it uses the DHT's protocol to determine its own ID in the network. This ID is usually a large number in the same space as the keys used for storing data. The node then asks the bootstrap node for information about other nodes close to its ID in the address space.
I see. So if we think of the DHT as a giant circle, each node finds its spot on that circle based on its ID. But how does it know which other nodes to connect to?
That's where routing tables come in. Each node maintains a routing table, which is essentially a list of other nodes it knows about. In many DHT implementations, like Chord, this routing table is structured as a finger table. The finger table allows a node to know about other nodes at exponentially increasing distances around the address space.
Finger table? That's an interesting term. Can you elaborate on that?
Sure. Imagine the DHT address space as a clock face. A node's finger table would contain information about nodes at 1 minute away, 2 minutes away, 4 minutes away, 8 minutes away, and so on. This structure allows for efficient routing because even if a node doesn't know the exact location of a target, it can forward the request to the node it knows that's closest to the target.
Ah, I get it now. It's like having a series of signposts pointing you in the right direction, with each signpost covering a larger distance. But how does this relate to actually routing messages or finding data in the DHT?
Excellent question. When a node needs to find a piece of data or send a message to a specific key, it uses its routing table to find the node responsible for that key. It starts by checking if it's responsible for the key itself. If not, it forwards the request to the node in its routing table that's closest to the key. This process continues until the responsible node is found.
That makes sense. It's like a game of hot and cold, where each hop gets you closer to your target. But what happens if nodes frequently join and leave the network? Wouldn't that disrupt the routing process?
You've hit on a critical point there, Sheila. This phenomenon is called churn, and it's one of the biggest challenges in DHT design. To handle churn, DHTs implement various strategies. For example, nodes periodically update their routing tables and use redundancy by storing data on multiple nodes. Some DHTs also use proximity routing, where they consider the physical network topology to reduce latency.
Fascinating. It seems like there's a lot of complexity behind the scenes to make DHTs work smoothly. Are there any real-world implementations we can look at to see these concepts in action?
Absolutely. One of the most well-known implementations is the Kademlia DHT used by BitTorrent. It's particularly efficient because it uses the XOR metric to measure the distance between two IDs, which allows for very flexible routing table construction and lookup procedures.
That's a great example, Victor. Now, I'm curious about optimization strategies. How do DHTs ensure that routing remains efficient as the network grows?
That's a crucial question, Sheila. One key strategy is the use of consistent hashing, which helps distribute keys evenly across nodes and minimizes the need for key redistribution when nodes join or leave. Another approach is to use caching and replication strategies to reduce the number of hops required for popular content.
It's amazing how much thought has gone into making DHTs scalable and efficient. Before we wrap up, let's reveal the answer to our quiz question. Victor, would you like to do the honors?
Of course. The answer to our quiz question is that in a DHT network with 1 million nodes, it would take approximately 20 hops on average to route a message from any node to any other node. This is because most DHTs are designed to have logarithmic routing complexity, which means the number of hops scales logarithmically with the number of nodes in the network.
Wow, that's impressively efficient. To summarize today's episode, we've learned about node discovery in DHTs, the structure and importance of routing tables, the challenges of handling churn, and some optimization strategies for efficient routing. We've also seen how these concepts are applied in real-world systems like BitTorrent.
Excellent summary, Sheila. I hope our listeners found this deep dive into DHT routing as fascinating as we did. Remember, understanding these foundational concepts is crucial for anyone looking to work with or develop decentralized systems.
Absolutely, Victor. And to our wonderful listeners, if you enjoyed today's episode, please visit crashcasts.com to find more resources and join our Discord community. Your support on Patreon helps us continue producing this content, and don't forget to subscribe and rate our podcast. Until next time, keep exploring the world of decentralized systems.